Well, good day to everyone joining us, and welcome to today's X-Talks webinar. Today's talk is entitled Wurster Fluid Bed Coating Batch Scale Aberrations. My name is Ryan Muse, and I'll be your X-Talks host for today. Today's webinar will run for approximately 60 minutes, and this presentation includes a Q&A session with our speakers. Now, the webinar is designed to be interactive, and webinars work best when you're involved. So please feel free to submit your questions and comments for our speakers throughout the presentation using the questions chat box, and we'll try to attend to your questions during the Q&A session. This chat box is located in the control panel on the right-hand side of your screen. And if you require any assistance along the way, please contact me at any time by sending a message using the same chat panel. At this time, know that all participants are in listen-only mode, and please note that the event will be recorded and made available for streaming on xtalks.com. At this point, I'd like to thank Coding Place, who developed the content for this presentation. Coding Place, founded in 1976, has over 47 years of experience in the pharmaceutical CDMO industry. This technology, along with feasibility studies, linear scalability, and product development services, enables Coding Place to provide customers with the highest quality services available in the Wurster fluid bed coating industry. They combine experience and expertise in engineering, development, and manufacturing to offer efficiency in the movement of a project from small-scale development into commercial manufacturing. Now I'd like to introduce our speakers for today's event. Charles Chuck Fry joined Coding Place in 1999 after holding R&D positions with Dow Chemical, Betts Laboratories, and Gilson Medical Electronics. Since joining CPI, he has been intimately involved with Wurster fluid bed coating formulation development, process optimization, scale-up validation, and commercial production. His primary interests include formulation strategies to meet product performance goals and elucidation of engineering principles and phenomena that influence fluid bed coating dynamics. Also today is Darren Kopp, who has 10 years of fluid bed coating and microencapsulation experience. He is currently a senior formulation scientist at Coding Place, where he leads and manages projects in the research and development department, which include formulating, design of experiments, technical transfer, and scale up to best suit the needs of CPI's clients for pharmaceutical, nutritional, food, and industrial products. But now, without further ado, let's go ahead and hand things over to our first speaker for today. Chuck Fry, you may begin when you're ready.
Thank you, Ryan. And welcome, everyone. The subject today is batch scale aberrations in fluid bed coating. We did a webinar, I think about a year ago, where we talked about scaling processes and so on. But when we talked about doing a follow-up webinar, one of the things that came up was the scaling factors that are involved. When we do something on a small scale and we convert it to a larger scale, sometimes performance changes. And our answer to that is typically, oh, that's just a scaling factor. And we want to elucidate that a little further, and that's what we're going to attempt to do today. And so, brief outline here. I'm going to focus on potential root causes of batch performance variance. And the bulk of this is going to focus on fluidization dynamics. We'll look at velocity differential, air and particle movement uniformity, batch size scaling, and air delivery uniformity. And then get into considerations around the nozzle and the spray factors, and a couple things about expansion chambers. And Darren will follow up with some case studies that show some of these scaling issues. So on this slide here, I show a diagram of a coater, and I'm assuming everyone knows something about Wurster, but just make sure we're on the same page. Up on the exhaust, basically position on the coater is where a blower would be located, and it basically pulls air through the entire system. And the air comes in on the intake, it goes up through the fluidized bed, where there's a differential velocity plate located at the base. And this induces a pneumatic transfer of particles up through a spray region in the center. And as the particles transport up into the expansion chamber, they then lose velocity, and gravity then pulls them back into a down bed region and the concentrically located around the up bed region. And as you run this process, it's like an engine. It just keeps running. Particles go up, circulate back in, and everything gets coated. But what we're going to look at today is we're going to focus on the dynamics of that fluidization. Partition factors, how air channels, and it's a very dynamic process. So it isn't always very clear how that works. I remember talking to a colleague who worked in the aerospace industry and talked about airflow dynamics in these systems. And the comment was, well, this is probably even worse than the aerospace industry, where often people have theories about how things work, but they actually have to put a wind tunnel in and actually do it to find out if it actually does that. So we have some challenges here. On this slide, this to me is the guts of the fluidization process. When Dr. Wurster started using fluid bed coating, or fluid beds for coating, at the time he was looking to coat tablets, but tablets eventually, the best process for those tends to be pan coaters, because they're less physically stressful on the particles, and so they're less prone to chipping and fracturing. But I have coated tablets before, and provided they're robust enough, it can be done in a Wurster. Now, in this particular application, the component in the coater was a caplet. It was about a 9/16 inch caplet. And if we look at the coater diagram on the left, the area of pneumatic transport is up the center. The area of just fluidization or particle suspension is concentric to that fluidization zone. And the dynamics of this, what turned out to be an optimal process, is related to the spread of the spray nozzle, how far the spray droplets transport. And when you have pneumatically transporting particles going up through here, within about an 8-inch diameter, all the spray is picked up by the particles. And so that was determined to be the optimal, diameter for the up bed. Any further increases in that has really no benefit, because the particles at the outer edge aren't getting coated as they're transported through there. Now, the other factor is the transport of particles from the lower outer edge of the chamber to the center. The fluidization air in that outer bed has to be able to create that transport so that we have no stagnant areas at the outer edge, where if particles are not fluidizing, they will not be coated. Now, the graph on the right is a look at what the pressure, static pressure, is in the outside the partition and inside the partition. And the dark line on the left of the graph is basically where the partition would be located, at least where the bottom edge of it is. I don't know what the full length of it was for this particular study. But if you look at the orange line in the graph, which is the outer bed pressure, right at the plate on the lower right corner, the pressure is going to be the highest. And there's an underlying assumption in this as well, and that is that the pressure immediately under the fluidization plate is the same across that entire underside of the plate, and the pressure immediately above the plate is the same across that entire plate. So if we look at the pressure and we move up through the down bed, which is the fluidization outside the partition, immediately there's low particle density because they are feeding into the up bed region at that point. But as you start to get to the point where the partition height is located, you end up with a steady particle density up through the rest of the bed, and so the pressure drop through the remainder of the bed is relatively linear. Now, inside the partition, the air starts at the same point in terms of pressure, and it very quickly drops because there's very little, any particle density right in the center. And so you get a very rapid drop in pressure. And then as you get into the partition region, the particle density throughout that region is roughly equivalent. And so you have a linear tracking of that pressure as well, but a different slope to the line because it has a different particle density. And it's actually lower because we're essentially diluting the particles out with all that up-bed air. When you get to the top of the bed, you get to the same pressure on both of those scales because they will come to the same point. Now, if you can grasp what's going on here, there are often questions about how far or where to mount the partition. Well, if you move the partition up or down, you can think about how it will influence these curves. So when you raise it, essentially the particles will basically feed in at the base more fully. It'll reduce some of the particle volume in that outer bed since it will feed more rapidly. And so you see a change in that pressure profile. And as you feed more particles in, when you raise it, essentially you'll see a change in the particle or the pressure profile for the up bed as well. And if you, another important factor is we often are looking at not using a full chamber. So if I were to have this chamber half full, think about what happens. Essentially that upper pressure wouldn't be as low. You wouldn't have as much pressure drop because there's less material in there. So instead of getting up at 18 inches above the plate, getting down below 2 inches of water, we might be somewhere up in the 6 or 8 inches of water range, and these curves will tend to come together. So it's these kind of factors, and if you continue to drop that bed to the point where the particle density in the outer bed is equivalent to what's going up through the center, there's really no driving force to push particles into the up bed zone. The air is free to move right up through the down bed. And so this is where you start to realize the importance of filling the bed so that we preserve that airflow and feed to the center. Now our chambers, quite often we work with cylindrical chambers as shown on the left here, and ideally you want to fill this chamber to near the top of the partition for ideal particle flow. There are systems out there, and we work with these as well, where you use a tapered chamber. And a tapered chamber basically uses gravity to physically feed particles back toward the center, so there's less requirements for that fluidizing air in that lower part of the bed. Essentially, the particles almost feed directly into the up bed. I've heard comments from people that often they never see any bubbling in the bed with a tapered chamber. And quite often we do see it with the cylindrical chamber. And essentially, when you are relying on gravity feed, you have particles near the wall of the chamber. Basically, the air isn't flowing up through those particles. It's just gradually feeding down with gravity. But there is likely some air going up right along the partition wall, perhaps not enough to make bubbling, but you can actually have bubbling, but it'll be confined to a narrow region, likely right along the wall of the partition. And depending on where you locate the partition, you can start to starve particle feed to the up bed. And this is where it's important that the partition be positioned properly to allow a free feed. Anytime you see bouncing in the bed or anything like that, that suggests that basically the feed is not uniform and it's varied, and it likely will lead to problems. Anytime you see a bubble, there's a chance there's not enough particle density to pick up spray, and you can start seeing spray build up on the sides of the partition because of lack of particle density occasionally, wherever that occurs. Now this is a little movie clip just showing a tapered chamber in the floor. And as you watch it, the thing to know is how long it takes a particle to go from the top of the bed, down bed to the top, about 5 to 6 video. And you also notice a little bit of bubbling in the outer bed over to the side, since the indicate that these are feeding in a little more favorably on that side. Right? And it could be an indication of things under balance. And it's hard to see if there's any bubbling near the. There's a potential rebound. Let's look at the logistics of this. We take apart this bed and we say it's 5 inches deep, and we dissect that. So the top of the chamber is 6 inches, chamber base is 4 inches, bed height is about 5. That puts the top of the bed at about a 5.7 inch diameter, and the diameter partition in the center is 2 inches. So you calculate some of these things looking at the volume of that outer bed, and we find that the volume of a truncated cone with that 5.7 and 4 inch diameter on each extension or each end, you come up with about 1,500 gram or milliliters of volume there. The partition volume in that region comes out to about 257, so you end up with a downbend volume of 1,261 milliliters. The bulk density is around 0.8 for these beads, then the downbed weight is about a kilo of material. And a kilo of material then travels through the spray zone about every 6 seconds. So from that, we can get a particle rate of roughly 12 liters, 12.6 liters per minute. And by weight, it's about 10.1 kilograms per minute. Spray rate is 20 grams a minute. That means we are wetting these particles at a rate of about 1.98 grams of solution per kilogram of particles. Another way to look at wetting rate is grams of solution per minute per kilogram of core. And looking at that, it comes out to 13.3. And if you take into account the solution solids, we end up with an estimated overall weight gain rate of 0.267% per minute. So 20 grams at 18% coat level, spraying at, or 20 grams per minute, 18% coat level. Look at the weight that it builds up coating on the charge, and we get that 0.267 number. Now that can be critical to an application, and quite often it's more sustained release type formulations or extended release formulations, where the way a film coat lays down will influence how it performs. So these can be important factors to consider when scaling. When going from a small to large scale, that weight gain rate can change significantly. And it might be important to bring that back together to a similar level. So let's look at the differential velocity assessment here. I've got a diagram here with the nozzle shown, obviously, there on the left side. You can see where the partition is located, and we see the particles feeding into that partition region. And in the outer bed, we've got the fluidizing area. And the air coming in that outer bed lifts and suspends the particles in the outer bed and also transports them into the upbed region. Now, what air is required to lift these particles? Often airflow can be inadequately set. If it's too low, these particles can drag across the screen and be subject to abrasion and whatnot. And if it's too high, you may restrict the flow of the particles in because you're pushing them up too high in the outer bed region. So let's just look at an assessment of that velocity, air velocity required to suspend the particles. Now I prepared here 3 graphs looking at the terminal settling velocity for spheres with varying specific gravity. So on the left, we're looking at 1.2 gram per cc for the spheres. Center one is 1.6, and the right one is 2 grams per cc. I also did 2 different temperatures to show temperature's effect on it. But basically, This information tells you what airflow you need to suspend particles. And it might not be clear immediately, but if you think about it, drop a particle in air, it falls, will eventually reach the terminal settling velocity. To suspend that particle, you essentially have to have the air moving in the opposite direction at that same velocity. And if you're looking at just a single particle, that works fine. Now, when we're working with a bed full of particles, each time, the more particles you have in that flow path, they restrict the air and they channel it down to the channels between the particles. And so just to see how that would lay out, on this table, I'm looking at 1.6 grams per cc particles. Just for example, I'll look at the 500 micron particle. Bed temp here is 77 degrees, and the terminal settling velocity is 564 feet per minute. So now if we look at a grid of particles, just the standard square grid particle arrangement, all the particles touching one another, the amount of area that it blocks to airflow is about 78.5% of that area. Sorry about that. So if we actually take into account the amount of open space, the actual velocity for the bed of particles comes down to 121. So if we have 121 feet per minute moving through that portion of the chamber, and when you put the particles in, you would have the right velocity to essentially suspend the particle. A staggered particle array blocks off 90.7% of that area, so it comes to 52.5 feet per minute of air to suspend a particle. An average of those two comes to 75.11. So when I look at these results and I compare them to projects that we have run, these fit really well with the data. So I think they are a good assessment of what's required for a spherical particle. Now we get into odd-shaped particles and jagged particles. We have other factors that enter in, so it's difficult to assess exactly what that airflow would need to be. But I used this in the last workshop webinar. But one way to do it is to put the partition in your chamber, and instead of having it distance off the plate, to actually push it all the way down to the plate to shut off all airflow that would enter the upbed. And then cap off the top of that partition with tape or some sort of cap that you tape down. Put some particles in the outer bed and start fluidizing air. And the point at which you start to see particles to fluidize and move around, take that air volume and divide it by the cross-sectional area of that whole zone, and that'll tell you the velocity that you need to lift those particles. So what does this mean for velocity differential now? So we're talking about the outer bed, just suspending particles, and what I just shared. But what is the air velocity in the center need to be? And generally, if you're doing things like granulating with a bottom spray Wurster, the velocity in the upbed, velocity of the air, is going to be roughly 3 to 5 times what it is in that outer bed to fluidize. And so when doing that, your particles, they don't feed in and necessarily go pneumatically transport directly up into the expansion chamber. They might, but they get into a wetter part of the stream where they're getting well wetted, and you're promoting that agglomeration. Now, if you wanted to try and do individual particle coating with a plate like this, the logical thing would be, well, kick the air up higher so that the particle flow goes into a more favorable position on the outer edges of that spray. And if you do that, you'll have problems there as well, because increasing the air there might give you enough velocity to transport up through the center, but you're also kicking up the air on the outside of the bed, and you're basically pushing particles to the point where they don't necessarily feed in very reliably. And quite often when doing granulations, the partition is removed. Now, if we go to the left side here, you'd have a high differential airflow. So attempting to show here is the particles flow more favorably in relation to the spray stream, and so they're able to be coated. Now this little film clip here shows there's basically a bore scope that's mounted to a screen in an 18-inch chamber. And the red line indicates where the nozzle position is on this. And the line on the opposite side is basically where the plate meets the particles that are flowing from the down bed. So if we watch this, one of the things to note on here is the fluctuation in the particle flow in here. So it's relatively free of particles, but the flow kind of dances around a little bit. Sometimes it comes in a little bit lower, and sometimes it's a little bit higher. Every time it comes low, it probably is getting into that lower part of the spray development zone. So it can be an area where it's prone to making agglomerates and that type of thing. So if you know that's happening, it's possible to increase the airflow potentially and address that issue and minimize the agglomerate formation. But there are other things that could contribute to improve this as well. So another thing you may be aware of, there are equipment manufacturers that have various means to basically provide a shield to force particles that come into the upbed to stay away from the spray zone until the spray is more fully developed. This is something in the IP from the University of Wisconsin. They had actually worked with that back in 1963 with a collar around the nozzle. And at the time, fluidization plates were adjusted to address issues associated with this. But as we've gotten into fine-tuning processes here at Coating Place, we've actually found that there are advantages when we're really trying to push the envelope on things to where a collar can be helpful in improving performance. Another scale concern is when we do scale, say down from this process shown on the right, and we go to a smaller chamber, like a 4-inch chamber, everything geometrically shrinks. And what you end up with is instead of say a 4-inch feed area for particles coming into the partition to get in the spray zone, we end up with closer to a 1-inch area. And the nozzle itself doesn't necessarily take up a small footprint. So this is an area where you can get some scale difference where particles are feeding directly into the spray and getting over wetted potentially, and you make more agglomerates on a small scale. And what we do to address that is we just raise the nozzle position to allow particles to be aligned more properly with the spray, and that seems to work quite effectively. So scaling fluidizing air, we've had clients bring in processes that were developed on a specific plate. We put in an equivalently sized plate, and it doesn't perform well. They use the same amount of air. And one thing to be aware of is if the velocity differential of the plate is different, you may have to adjust the air to get an equivalent performance. So on this particular slide, what I'm showing is the A plate is, say, the benchmark plate, square foot of plate area. 100 CFM gives a good process. If we go to a different plate and has a, say, a 12-inch velocity or a 12-to-1 velocity differential, 100 CFM will not be equivalent in that we'll have more air in the upbed because of that higher velocity. And so we'd end up with less air in the outer bed than would have been in the original plate. And the best way we address that is to adjust for that velocity differential by, if we want to scale to the down bed, it's multiplying the original airflow by the new velocity differential over the old, and 120 CFM would give an equivalent performance in the outer bed. Now, if the up bed is the critical part of the process, then you would actually scale the air down to try and match that. But I know velocity differentials are difficult to determine. Simplest way I know is to look at up bed air velocity versus down bed air velocity. Upbed air volume rate divided by the area of the upbed will give you what the upbed velocity is. Downbed air volume divided by the downbed area would give you the downbed velocity. And this would be equivalent to percent of air entering the upbed over the percent of the bed area in the upbed would give you that velocity, and vice versa for the downbed. So if you know the amount of open space in the upbed region, you can, and the total amount of air, open space in the plate, you can calculate how much air enters the upbed. And you can also, the remainder of it would be going to the downbed, and it allows you to get that velocity differential. Now be aware this is strictly based on area. In actual practice, the air partitioning will deviate a little bit from this due to the friction factors going through holes and perhaps the pitch or distance between holes and that type of thing. But this offers a good estimate of where it can be, and it works really well for comparative purposes from one plate to another. At Coating Place, we work with this range of chamber sizes. And as long as the velocity differential for a plate is consistent, and the proportion of upbed to downbed in that plate is consistent, air will scale linear with the diameter of the area of the plate. So we'll go from say a chamber with a 4-inch base to a 6. 2.25 times the air will be good for that. And you can see all these red numbers indicated on here, what the scale up factor would be strictly based on the area of the fluidization plate. When we get into multi-nozzle units, we are at a position where we're ganging together multiple 18-inch units basically. And so when you get to a 3-nozzle unit, it's 3 times the air. When you get to a 7-nozzle unit, it's 7 times the air. Now, when you scale from small to large, the depth of the bed changes. We're not able to keep the same bed depth on a small scale as we are on these bigger chambers. So when it gets into the weight gain rate associated with these, that type of thing, they don't always track with this. When we are working in an 18-inch chamber and we jump to do the 3-nozzle, if we keep the partition length the same and the position the same, and the same thing with the 7-nozzle unit, then the 3 times the air also translates to 3 times the material as well. So it's a very consistent process. 3 times the air, 3 times the amount of material, same spray rate for the 3 nozzles, and you end up with the same weight gain rate and coating factors associated with that. So it's a very scalable process. Now, I mentioned earlier the importance of uniform air delivery to the plate. And one of the challenging areas of a fluid bed is the air typically comes in horizontally to the plenum region, and then it has to turn to go vertically through the plate. And depending on the design of that, there's a good possibility that the air will kind of channel into the far side of that plenum region, and you'll end up with an area of higher pressure on one side than on the other. And that can really skew the results in a coating unit, because now you've got the fluidization that's occurring on one side is different than that on the other. And it can actually skew the particle flow into the spray stream on one side, where it might be hitting in a poorly developed region of atomization, where the other side is very favorable. It also has the potential to actually skew the spray pattern and start pushing to one side. So if you ever see any buildup of coating material on one side of a partition, or maybe if you're using really strong airflow on one side of the expansion chamber, it could be indicative of not having a uniform delivery to the lower side of the plate. What we do is introduce an appropriate device into the plenum region to address this issue when it is a problem in a process. Another thing to address is plate porosity. If the porosity, the plate is too porous for the amount of air moving through it, then you have a challenge in that the particles and how they weight on the plate will influence where the air goes. So you get a less uniform delivery of air to the actual particle bed. And in some of the reading that I've done, it indicated for large fluid bed processes, the pressure drop across the plate is around 2,500 pascals or higher. That's about 0.36 pounds per square inch. And for a lot of the Wurster plates, quite often we're not dealing with pressure drops across the plate that are that great. It's also, I haven't done the logistics on it, but it's possible just the act of inducing this differential airflow, it's not possible to get to that and have a viable process. That's just something to be aware of. If you jump from a process that's working with one level of plate porosity to another, even if the velocity differential is the same, there could be a difference associated with that difference in porosity. So this is an interesting assessment, and what I did here is I looked at the air velocity in feet per minute above a perforated plate versus the hole diameter that's used to make those perforations. So if you look at the title here, it's a square pitch hole pattern, as shown on the over on the right here. The thickness of the plate is 12 gauge, about 0.1094 inches, and the pressure drop through the plate is 0.08 psi. But it's interesting to see how the size of the hole used to make the plate, even though you have the same amount of porosity, influences what you actually get for velocity. And so those are factors. If you really want to tune something up, they can be an important part of this. Spray rate scaling, atomization is, I look at 4 factors for scaling spray rate, depending on what's critical. If droplet size is important, atomization's concerns might be at play. And depending on nozzles and how well they scale, it's possible to get the size on one scale compared to another. You might have to use a different pressure. When you are using different pressures, you're going to be introducing different physical forces on the particles. And so you can get to variations associated with how much you beat the particles up with that. Drying capacity is about the capacity of the air to remove the vapors of a solvent that you're using. And sometimes matching that is critical. It is a water process. Relative humidity, either of the air at the temperature you're working at or the air with additional water sprayed, might be critical to the process. And as mentioned earlier, weight gain rate can be important, and I generally see that more with extended release coatings. But the graph on the left here shows spray rate versus bed temperature for 20% of drying capacity using 40-degree dew point process air at 18% solids. And thing to note here, there's the blue line is for a 18-inch chamber loaded with 52.8 kilograms of charge and using 540 SCFM of air. The lower line is a 60 CFM of air in a 6-inch chamber and a 2-kilo charge. But these two conditions would match the drying capacity concern. Now, if you take these same two conditions and you plot them based on weight gain, you find that the 6-inch chamber has a much higher gain rate compared to the 18-inch chamber. And that's because that charge that's in the unit doesn't, the volume doesn't scale linearly. It's more the airflow is only scaled to the area of the plate. So if weight gain rate is critical, may have to bring these lines close enough together to address the needs of the process. Nozzle scaling at CPI, we scale to the fluidization plate size. So if we have a CPI 6 nozzle, it's designed for a 6-inch plate. Our 2 nozzle has been around a long time, but it's actually scaled for an 18-inch plate. But if you scale the airflow on matching air differential plates, basically when you scale the spray appropriately, the same pressure gives approximately the same droplet size. So you have a comparable sort of atomization stress associated with the process at the various scales. And again, I mentioned we use an adjustable nozzle height to optimize the relationship of spray and particle. So last thing I'm going to look at here is expansion chamber factors. We use filter pulsing with our systems, and we can vary the pulse frequency and the pressure on these. One of the concerns with the pressure, and the reason we offer different pressures, is when you are working in a smaller unit, you put 100 psi pressure on the filters and that pulse takes place, you can see a compression of the bed in the coater in the spray zone. And so you likely are going to influence what happens there. So we try to eliminate that compression of the bed when we operate. Surface area. The surface area of the coater and the expansion chamber compared to the amount of material in the bed can be critical. On a small scale, if you have electrostatic charge and particles hanging up, you might have, say, 30% of the material that wants to hang up inside the unit. And if that happens, then the remaining 70% is getting coated, but not accounting for that in the coating application, your coat level is much higher than you expect it to be based on theory. If you go to a bigger coater and it's only a 5% hang up, obviously you get a different performance based on those two. And the other thing is this slope on the expansion chamber. We strive to maintain the same relatively steep slope to the chamber wall on all of our units. And when that does get to be a more flat surface, you can end up with more particles hanging up in there, and that can skew results from one scale to another. So that's the extent of what I have to offer. If you are interested in looking at gas fluidization technology or how these fluidization principles work, I found these two references here to be very helpful, and I pulled some of the equations that I used from these as well. So with that, I will turn this over to Darren.
Okay, thanks, Chuck. So I think, as most of us know, even if you take into account all the things that Chuck has just talked about, things may not go as we expect. So I wanted to just touch on a few projects where scale and transfer to our equipment at scale has unpredictable effects. Project A here was a proof of concept project. We had goals to improve yields and hit target spray rates for the process, kind of like most projects would like to do. So some of the unique challenges here were the small particle size we were working with. There was a high drug load. There was a low amount of binder in the initial formula. Some of the initial conditions that were provided to us by our client were attempted to match at our 1800 scale to start. And after a couple of attempts, we realized that we may need to characterize that drug loading process a bit more to make this viable at even larger scales. As you can see, we're getting in this 15% fines or undersize, and our yields were in that low 80s. So to better characterize that drug loading, we scaled back down to our 900 units, and to get more out of the remaining materials we had on hand. We also made a couple of changes. One of the big changes was to the fluidizing air plate. The new plate design that was used at the 900 was with an airflow pattern that increased airflow differential so that it was more favorable for the small particles we were working with. We also increased our spray rate to provide a wetter coating condition to help reduce the fines even further. After several attempts, we were able to settle in on conditions that, if scaled up, would end up meeting the yield and spray rate targets that we wanted to see. I guess just to give an idea of the scales I'm talking about as far as materials concerned, the 1800 charge weight was around 10 kilos, and then after the high drug load, we end up around 66 kilos. So we start out kind of very low with chamber capacity and then fill it out. That kind of carries over to the 900. But the charge there was 3 kilos, ending around 20. We then were able to take those optimized conditions at the 900, work our way back into the 1800. We would take that same plate design used at the 900, but we were still seeing kind of high amounts of fine material. So we thought this was odd, so we ended up pushing the spray rate a bit more to reduce those fines. Then we started seeing oversize or agglomeration. The fines never went away, so it's never great to have both. Typically, you're gonna have one or the other. So we ran some additional batches, but we can never overcome that problem. At 7% was about as good as we could get with either one. So at this point, we were kind of led to believe, the fines were then being generated by the actual physical stress on the beads, or that actual weight of material or particle to particle interaction inside the chamber, kind of being an issue with the low amount of binder that was there. So that's kind of where we focused on to resolve the issue. We had to end up modifying the formula, which is kind of a last resort in most cases here, and we increased the binder. So once that binder was added, we ran a few more confirmation batches at the initial scaled conditions from the 900 work, and we're able to reduce the oversize and undersize to around 1%, getting us kind of back into that where you want to be as favorable process outputs. Project B was a technical transfer. They had some goals of optimizing process times and outputs, as most projects do. Some of the challenges here were that there were multiple coatings, the third coating being the most challenging. And also, when it came time to manufacture GMP campaigns, we ran into an API shortage. So this caused us to reduce our initial charge size, thus reducing overall chamber capacities along the way, or another way, changing that scale within the unit. We had done several development campaigns at initial scales, and it developed what we felt like was a very robust process. Outputs were becoming very predictable. We knew what was going to happen at that chamber capacity. As you can see here, the initial two coatings process very much the same when charge amounts were reduced. Chamber capacities were reduced by about a third. The spray rates remained the same, so this kind of increased our gain rate, or the wetting rate that Chuck had mentioned. But we didn't see any effect in these outputs, so that was great. The third coating, again, the most challenging coating, just from the nature of what was being applied, showed an increase in oversize by about 10%, thus reducing our yield by 10%. And just kind of looking at that, we attributed the changes here to the gain rate. That when we scale this process up, that's kind of what we'll be looking at. We'll be kind of coming back to a larger, more full chamber, and hopefully that will then reduce our oversize back to where we were before and improve the yields. And we may even be able to push that capacity even higher, and then we can scale up without sacrificing spray rate or process time. The last project here I wanted to talk about was another technical transfer, and then a scale up. So keeping their current processing parameters the same as they were at the previous site, specifically spray rate, because it was very fast. Again, big challenge here was spray rate. It's particularly high for the airflow that we needed to match at the scale of the equipment we were using at CPI. So we started out with the initial conditions and found out very quickly we couldn't reach that, the 500 gram per minute target that we wanted. and we had to stop the first batch short of that. And when we hit about 300 grams a minute, we saw some oversize, and this was kind of metered up into that 300 grams a minute, and just to observe how things were going in this coating. So we knew to improve our chances of a successful scale up, we'd have to make several changes at the 1800 scale first. We ended up modifying our nozzle design to provide more air volume but maintain a lower pressure. So this could help our droplet size and hopefully the oversize. We also modified the fluidization plate to increase that airflow differential while maintaining a similar air volume. And lastly, we incorporated that nozzle collar that also Chuck had mentioned to help push the bees into a more favorable coating region. So all of the changes were then made and implemented. And after running the batch, it showed that we were successful. We hit the target rate, didn't generate a lot of oversize. The conditions were confirmed then again at the 1800, and we were able to perform our linear scale to our 3 nozzle unit with no issues. And maybe in this last project might necessarily be like we saw issues during the scale up, but try to prevent those issues at the small scale. So showing kind of how important it is to do the work at a smaller scale prior to scale up. And I think that's all I got. So thanks for listening. And I think at this point, if there's questions, we'll be taking some of those now.
Yes, well, thank you both for that very insightful presentation. I'd like to invite the audience right now to continue sending their questions or comments using the questions window for this Q&A portion of our webinar. Now, I've already received some questions for you, so we'll get ourselves started with those. The very first question that I have here for you just says that in the air velocity versus hole diameter graph for the perforated plates, larger hole diameters resulted in lower air velocity. Is that correct? And they feel they expected the opposite.
Yes. Yeah, if I can go back to that slide, that might be helpful. I know I went through that one kind of quick. Push that back my way or not, Ryan? Sure, I can share my screen. Farther back than I thought. Yes, I think that is a good question. I elaborated over that as well. Now, when these curves were generated, they were based on equations in the reference cited here. And this took into account the pitch or the distance between holes, as well as the discharge coefficient associated with that array of holes. And the pitch actually has a significant factor here, and that distance between holes basically is in a denominator position. So as it gets larger, you see a lower air getting through. And I think that's just because if you think about air pressure over an entire plate, and as holes get farther apart, you have a lot of area where there's just no holes for air to go through. And when it's made smaller holes, they're in closer proximity to one another, and they actually are able to carry the air through more freely. So I think basically that those factors outweigh any frictional factors associated with air movement through a smaller hole, and this is what results. I've never confirmed these results. These are just calculated based on the principles outlined in that chapter.
Right, so, very interesting. Thank you very much for that breakdown. I'm sure they appreciate that. The next question I have here is curious, what are the lower and upper capacity limits for a coater?
Often get that question. The way I look at it on the lower end, if you're looking at strictly the fluid bed dynamics, I would say a chamber that's roughly a quarter filled is what seems to be a good lower limit. And this is based on years ago, there was some work done in a single nozzle chamber And the charge weight that was put in the coater was decreased successively down until the point where the coating efficiency started to drop off. The coating efficiency, I'm talking about the basically how much of the coating actually gets on the particles and how much is spray dried. And they found roughly at about a quarter of chamber capacity filled, you started losing efficiency. And I think that's attributed to you eventually get to a point where there's inadequate particle density within the coater itself. And so that all the spray is not picked up by the particles. And so you lose that efficiency. On the upper end, on a small chamber, it's, I think, pretty much staying within those geometric equivalents in terms of the height of the chamber to the diameter of the chamber. As you get into the 18-inch chamber and higher, I'm not sure what the upper limit would be. For most systems, there's a blower capacity, and the blower capacity is probably going to create that limit. So you could probably go to a deeper bed and put more material in there, but the blower probably wouldn't be able to handle it. And beyond these things, it'll be equipment concerns. It'll be things like a charge hopper and how much material will fit in that, or a discharge container and what fits in that, or perhaps a solution vessel and how much solution will fit in it. But that's just a general answer I can give to that.
Excellent. Thank you very much. The next question here is curious, how do the airflow dynamics change if the partition is not used?
Oh, good question. That was something done Coating Place years ago, where I think they were working on a process early in development phases where a partition was used, and in the original patents, it's more the differential airflow that is the key of the patent. The physical partition is not necessarily required. But as they continued to increase the height of the partition, or the gap under the partition, they saw it really didn't change the results for a process. And so they eventually took the partition out and found they got the same results with or without a partition. So the way it changes the dynamics, though, I think, is if you think about removing that physical wall between the up and down bed, it pretty much is open for particles to come into that up bed zone anywhere along that pressure gradient. And so you'll get a more free flow of material in there. I think typically you might not need quite as much air in that system, but you'll also see that bed kind of collapse depending on how deep the bed is. And so you may have some issues in how deep you can go with the bed. But yes, it can be run with or without a partition.
Wonderful. Thank you very much for that answer, for all of the answers and your time here today. But we have reached the end of the Q&A portion from our webinar. If we couldn't attend to your questions, though, the team at Coating Place will follow up with you. Or if you have some further questions, you can direct them to the email addresses and phone number that's up on your screen. I want to thank everyone for participating in today's webinar. You will be receiving a follow-up email from X-Talks with access to the recorded archive for this event. A survey window will be popping up on your screen as you exit, and your participation is appreciated, as it will help us to improve our webinars. Now, I've also sent you a link in the chat box, and with this link, you'll be able to view the recording of this event on this page, and you can also share this link with your colleagues so they may view it once they register for the recording here as well. So I encourage you to do that. Now, please join me once more in thanking our speakers for their wonderful time here today. We hope that you all found the webinar informative. Have a great day, everyone, and thank you for coming.